Good morning, everyone. My name is Matt Grigori, and I manage the Customer Solutions RD&D team at SoCalGas. I want to thank you all for joining us today for another SoCalGas RD&D research webinar featuring our recently completed demonstration of gas heat pump technology with the California Energy Commission and GTI. Today's webinar is part of a regular series of events where the SoCalGas RD&D team shares the results of our research projects with key stakeholders in the energy research community, as well as the general public. SoCalGas is taking proactive steps to become one of the cleanest gas utilities in North America. The SoCalGas Research Development and Demonstration Program plays a key role in this effort. Staffed with experts in science, engineering, environmental policy, and market transformation, the RD&D program develops new products and technologies that reduce costs, save energy, increase safety and reliability, improve air quality, and reduce greenhouse gas emissions. The RD&D program supports research across the entire natural gas supply chain. On the supply side, the Low Carbon Resources Program focuses on the production of renewable natural gas and low-cost, low-carbon hydrogen to replace conventionally sourced gas. The Gas Operations Program focuses on supporting gas transmission, distribution, and storage operations. And at the end of the supply chain, the Customer Solutions team develops technologies for all of our customers using natural gas and hydrogen to power their homes, businesses, and vehicles. This team addresses technology development under the Clean Transportation Program, the Clean Power Generation Program, and the Customer and Use Applications Program, which supported the research being presented today. SoCalGas RD&D subject matter experts collaborate closely with universities, national laboratories, public agencies, businesses, and our own customers to move important new technologies from the lab to the market. The RD&D team coordinates with researchers in California and from across the United States, supplementing and complementing the work of other public agencies such as the California Energy Commission and the Department of Energy. In 2019, the RD&D program invested more than $13 million in energy technology projects designed to improve safety, reliability, efficiency, energy choice, and resiliency for our customers and energy consumers throughout California. On average, every dollar provided by SoCalGas RD&D was matched by $5 of external funding support. For more details on the RD&D program, please visit our website where you can download our annual report, which includes a comprehensive list of projects, and find information on upcoming webinars like this. And feel free to email the team at rddinfo@socalgas.com. We want to hear from you. Finally, in support of the California Public Utilities Commission's Environmental and Social Justice Action Plan and General Order 156, SoCalGas RD&D is dedicated to improving the quality of life for all of our customers, maintaining a diverse workforce, and working with suppliers that represent and reflect the communities we serve. This webinar is just one of the ways we are working to engage and educate the public about the RD&D program. And now I'd like to welcome Jackson Thatch from the California Energy Commission to provide a few remarks.
Thanks, Matt. I'm not seeing the slides on my end yet.
Is anybody seeing slides? Okay. There we go. How's that?
Okay.
Much better. All right. Well, I'm hoping that our attendees can see what's going on.
Okay, here we go. All right, good morning, everyone, and thank you so much for having me here. My name is Jackson Thatch, and I'm a mechanical engineer from the Energy Research and Development Division in the California Energy Commission. Oops, sorry. Apologies. Okay, so what I wanted to start off with is going over California's clean energy goals. We've set goals to achieve a decarbonized energy system and economy by 2045. We plan to do this through advancing clean energy supply and increasing energy efficiency and load flexibility. And we also want to address affordability and equity in order to achieve market penetration into vulnerable communities that are typically found in low-income and disadvantaged communities. And finally, we want to increase grid resiliency by increasing grid responsiveness and flexibility in order to anticipate, manage, and mitigate risks. Oops, sorry. Okay. This slide gives you a summary of the driving programs that we use to invest funds in order to achieve these goals. In addition to the natural gas program, we also fund electricity through our EPIC program, and there's also food production and low carbon fuels research and development. In total, we fund almost $300 million annually, and these programs help to take innovations from the early stages of R&D, the prototypes and the proofs of concept, the pilot testing and demonstrations, and then we bring them into early adoption and scaling until they finally reach market maturity. So our natural gas program started in the late 1990s. This program focuses on investing technologies and solutions that promote a more reliable, cost-effective, safe, and equitable energy service for natural gas ratepayers while also supporting California's energy and environmental goals. We have around 90 active projects with an annual funding of $24 million, and the main research areas are listed here. So we've awarded funds to a wide variety of organizations in both the private and public sectors, including national labs, industry groups, private companies, local governments, universities. We're committed to ensure that a diverse range of applicants have the opportunity to participate, including small businesses, women, minority, LGBT, and disabled veterans. The portfolio of these projects range from pipeline improvement and integrity to decarbonization, to gas heat pump water heaters, one of which you'll hear about very soon. So we encourage you to connect with us through various social media channels such as Twitter, LinkedIn, Instagram, and also through our Empower Innovation platform. This platform was created to connect and support energy innovators such as entrepreneurs, funding providers, universities, local governments, businesses that are deploying and demonstrating new energy technologies. Here you can view upcoming events and opportunities that you can express your interest in, and also see others that have done so as well. And then you can connect with them and message them with potential partners. So I encourage you to check it out at empowerinnovation.net. And then before I hand it back, I do want to highlight two opportunities that we have coming up. The first is a staff workshop for our EPIC interim investment plan to discuss preliminary research themes and initiatives for the interim investment plan for the 2021-2022 year. And the second workshop is for our natural gas proposed budget to seek stakeholder thoughts, comments, and feedback on the proposed natural gas research initiatives for the 2021-2022 fiscal year budget plan before it is submitted to the Public Utilities Commission. The research initiatives presented in this budget plan will ensure that the Energy Commission's natural gas research program continues to provide energy leadership and innovation necessary to carry out California's progressive energy policies and inform decisions and actions to local, state, federal, and international levels. Both workshops are tentatively scheduled in January of 2021, with the former in early January and the latter in late January. So be sure to check out these links for the latest updates on these events. And then finally, here's my contact information in case you have any additional questions or follow-ups. Thank you, Matt.
Thanks, Jackson. So before we begin, a few housekeeping items. There will be time for a Q&A after the presentation. During the presentation, please submit your questions in the GoToMeeting question box. A recording of today's broadcast will be made available to all attendees and will be posted on the SoCalGas RD&D website. And we want to make sure our research webinars are valuable to the broader R&D community. After the webinar, you will receive a brief survey request. Please let us know how we are doing and what we can do to improve your webinar experience. Your feedback is important to us. Now I'd like to introduce our presenters. First up, Mary Sweeney is a senior market analyst in GTI's Building Energy Efficiency Group. Her expertise lies in market screening analysis and segmentation for natural gas technologies with a special focus on energy efficient and emerging technologies. She performs programmatic benefit cost analyses for utility research and development programs, assessing the value brought to ratepayers. For 7 years, she has served as the lead program analyst for the NICOR Gas Emerging Technologies program. She holds degrees from the University of California, Santa Cruz, go Banana Slugs, and the University of Michigan. And we also have Paul Glanville. He's an R&D director in GTI's Building Energy Efficiency Group, delivering solutions for a safe, efficient, and environmentally responsible built environment. His work with industry and academia has resulted in numerous products, patents, and publications. He has prior experience in air quality management and holds degrees in mechanical engineering from UC Davis and the University of Washington, specializing in combustion science. He is active in ASME, ASHRAE, and ANSI CSA, and all sorts of other acronyms, and is a registered professional engineer and remains both a data geek and a tinkerer. So welcome, Mary and Paul. We're very excited to see the results that you're going to present today.
Great, thanks, Matt. Should I have control at this point?
I think you do.
Okay, great. So before we dig into the specifics of the project, I did want to provide a little context about our motivation for research in this space. Looking at the residential water heating market, there's a significant retrofit potential here. I have a graph on the screen that shows the main water heating fuel per housing unit for the 50 largest US metro areas. Within each bar, you can see the blue component represents gas-fired water heating and the orange outline component, electric water heating. So you can see there's certain regional variations here. Ultimately, gas represents about 62% of overall residential water heating. If you remove from this graph Florida cities, then it actually becomes a 2-to-1 ratio of gas to electric water heating. For homes in mild climates, coastal and Southern California, for example, water heating is often the largest natural gas load in the home. Ultimately, again, looking specifically at California, about 3/4 of the homes in the state have gas-fired water heating. About 95% of those homes have minimum efficiency storage tank water heaters. So there is some real potential here for market transformation. I just want to make sure, there we go, okay. So residential water heaters are really an appliance that homeowners expect to install and completely forget about. This is a type of appliance that is not typically maintained, and most sales, about 82%, are emergency replacements. So their life expectancies range between 8 and 12 years typically, and over 1/3 of them are currently 10 years old. So we have a significant stock that is ripe for soon-to-be emergency replacements. Likewise, this is an opportunity, a significant opportunity in California to support the push towards building decarbonization by removing some of those minimum efficiency units and having a significant efficiency jump with a gas heat pump water heater. But as many of you who are familiar with the residential water heating space understand, this is a chronically difficult space. The value proposition is challenging. A typical homeowner spends a couple $100s a year on hot water, and oftentimes efficiency improvements come with significantly higher upfront costs, which make the economics really challenging in many cases. Likewise, this is sort of unique in the sense that if a homeowner is going to be a do-it-yourself installer, they're likely to do it with water heaters, more likely to do it with water heaters than other gas-fired appliances like furnaces. So you actually have a 50-50 split of sales through distributors versus retailers. So there can be challenges about how best to promote efficiency. And ultimately, touching upon something I mentioned from the previous slide, reliability is key. You need 10 plus years of operation with minimal maintenance. And as I mentioned, because you have significant do-it-yourself installs, again, making something that is simplistic and straightforward enough for a homeowner to install and maintain if necessary is important. Looking specifically at this project, our primary goal here was to support the commercialization and deployment of a gas heat pump water heater, beginning on the critical California market, where approximately 1 million gas water heaters are sold each year. But breaking this goal down further into some more detailed objectives, we intended to demonstrate 5 fourth-generation gas heat pump water heaters in single-family homes in the Los Angeles Basin. We're going to be quantifying energy efficiency, emissions, and reliability through performance and extended life testing in laboratories. Likewise, we engaged in some efforts to prepare stakeholders and code officials through information sharing, the development of simulation models and analyses. And we also wanted to better evaluate and understand any barriers to market entry and commercialization in California and nationwide. And of course, as with any field demonstration with a pre-commercial unit, we always intend to gather any feedback from end users, in this case, installation contractors as well as homeowners, that can help inform any needs ahead of commercial introduction. And I will say that obviously you could see this was very much a team effort. We have the logos from the project team that executed this project, funded by CEC, co-funded by Southern California Gas, and several other project partners there. So, bear with me, I'm having a hard time getting the slides to advance. Okay. Oh. So for the field,
That is my fault.
It's okay. For the field demonstration approach, of course, anytime we go into the field, we're always thinking about monitoring for energy savings, but there were several valuable inputs we wanted to gather from the field evaluation beyond simply the energy savings. We did want to get site-specific savings, and we wanted to be able to better assess reliability issues. Likewise, we wanted to be able to normalize the savings that we saw in the field, as well as the behavioral conditions, and use those to be able to develop a general case that could be adapted across California's climate zones and other applications. We wanted to understand, as I mentioned, the impact of installation barriers. What was the ease of retrofit? What was the plumber experience? What kind of additional support and education and training is likely to be necessary for the contracting community. And of course, we also wanted to quantify host comfort in addition to qualitative questionnaires to understand things like performance and noise. We also wanted to look at the data and see if there was any evidence of capacity issues related to running out of hot water. Looking for opportunities for innovative controls and understanding how best to apply any necessary supplemental heating. Looking specifically at California, of course, we also wanted to look at NOx, as well as certain other requirements in the state that we have here related to seismic strapping, as well as the flammable vapor stand, that 18-inch stand that several people are familiar with, that you have to place your water heater on. So we looked at these additional components as part of our field evaluation. As I mentioned, we placed 5 units in the field. You can see here the blue circles numbered 1 through 5 and the map on the right. So we sort of had 2 clusters, kind of an inland cluster and a coastal cluster. Likewise, we had a 6th unit that was installed at SoCalGas's laboratory at their Engineering Analysis Center for some additional extended life testing and performance testing. The units in the field were in operation for just over 12 months, so we had a significant data set there. With that, I'll pass it over to Paul. Paul, I do not see a function for giving you control.
I think I just got it. So thank you,
Okay,
Mary.
great.
I was the principal investigator on this project, and as Mary noted, it was a large team. But before we get into the results from the demonstration side, let's talk about what is the gas-fired heat pump water heater. First of all, it has a similar form factor to other heat pump water heaters you may be familiar with. It's integrated. The heat pump and the tank are one package, and the tank is usually larger than the products that it's replacing, because the output on a hot water basis is a little bit lower from the heat pump. So we need to have a larger tank in order to accommodate that reduced thermal capacity. And that's mainly because we want to limit the size of the heat pump. We want to limit the amount of refrigerant needed for this process. So as a heat pump, if we just use some very simple math here, providing 1 unit of hot water, some fraction of the energy that we put into the process is going to come from the energy grids. For natural gas heat pumps, it's going to be from the gas grid and also from the electric grid. For electric driven heat pumps, it's just going to be from the electric grid. But as a heat pump, it's going to be upgrading some amount of ambient air, usually where the heat pumps are installed, and upgrading that ambient energy to usable hot water. So that's how we get those efficiencies, or as we call them, COPs, coefficients of performance, greater than 1. On a site basis, the COP for the gas-fired heat pump water heater tends to be between 1.4 to 1.8. We'll dive a little deeper into that later on, as compared to electric technologies that tend to have COPs between 2.5 to 3 on a site basis. Now, if we take this a little bit further, these products, they want to meet those high demand scenarios, multiple showers at once, or in the future, maybe we'll go back to having many house guests. So you want to be able to accommodate that increase in hot water load. These products tend to do that through supplemental or auxiliary heating. And in both cases here for this project and for most conventional electric heat pump water heaters, this is a immersed electric element. And just in rough terms, this can provide between 15 to 40% of delivered energy or less. And we'll talk about how we measured those results in this study later on as well. But just from the high view here, because really this is an efficiency play, the primary reason to buy a heat pump water heater is because you want to cut your energy and carbon impact of hot water generation. So if we look here at the, just for the 100 gallons of hot water produced in California using some kind of a back of the napkin estimate here, you can see that from a source energy basis, from a greenhouse gas basis, we end up nearly in the same place for both technologies. So really we're aiming for, if a customer wants to increase their efficiency or reduce their carbon footprint or both, and they can go from standard to heat pump, that there's going to be a fuel-fired option in the near future. And then some of the bases of these estimates are shown here as well. Getting a little more into specifics here, this is part of a partnership that GTI has had with Stone Mountain Technologies, an absorption heat pump startup company based in Tennessee, which has looked to develop an OEM supplier model where they will be developing and supplying the guts of these types of products, the absorption cycle, the vapor absorption cycle, that is, as deployed in heat pump water heaters or even larger equipment for space heating or for commercial space heating or commercial hot water as well. A lot of statistics are shown here, but just to show you where we are, we're on the left-hand side here. So this is a 10,000 BTU an hour, 3 kilowatt output nominal heat pump. It's got about a 6.5 thousand BTU an hour input or 2 kilowatt input. The burner is about the size of my thumb. It's a rather small, efficient design developed a few years ago. And this product has a projected efficiency or uniform energy factor between 1.2 and 1.3, depending on the tank size. As a retrofit, what these products will encounter with those low efficiency water heaters that Mary noted before, a 1/2-inch gas line will be more than sufficient. As far as venting goes, you'll see later in some photos, these use 3/4 to 1-inch PVC for the low temperature condensing efficiency venting. These were certified as ultra low NOx as part of this program. So that's a good thing for California. And these do consume electricity, not only to run the heat pump itself, but also that supplemental heating mentioned before. This is sized to operate on a 15 amp, 120 volt circuit, which is what most products would encounter in a garage or basement type installation. Physical size is shown there, and these products use ammonia as the refrigerant, which is, or R717, zero ozone depletion, zero global warming potential, and it's about a charge of a little over 1 pound. So it's permissible for indoor installations. Some of these larger equipment over the right-hand side here, these necessarily have to be outdoors due to that ammonia charge. So leading up to this project, we really had two sets of efforts, and I'm going to go through them quite quickly here and pointing you to some resources if you're interested. About a decade's worth of research and development initiated with the Department of Energy and carried forward through support from the gas industry and a number of manufacturing partners have helped SMTI and GTI get to the point from the laboratory up through these pilots and demonstrations. As a result, we're calling these the products in this project fourth generation. They represent a significantly different version of 4 times over from what was operating in our laboratory about 10 years ago. A lot of lessons learned, a lot of effort to get to this point. So there are too many partners to thank here, but really appreciate all that got us to this point here. But worth pointing out is first, what is underneath the hood, so to speak. This is a simplified believe it or not, it's a simplified diagram of the absorption cycle. It uses a single effect ammonia water vapor absorption cycle, a process that's been known and in practical use for about 150 years. And this was originally used in the production of ice before widespread electrification in the 19th century. And really what this does here, first of all, we shrink this down and we place it on top of the tank. Everything shown in this diagram here is in the top of the tank here. You can see where it integrates with the tank over on the right-hand side. But I'll draw your attention first to the condenser, the expansion valve, and the evaporator. These are common components with vapor compression type heat pump water heaters, which are the more common products out there. And because we're using the refrigerant here, this is a nearly pure refrigerant here, ammonia, cycling through these components. Ambient energy is absorbed at the condenser, and it's yielded absorbed at the evaporator, and it's yielded at the condenser as useful heat. Everything else that you see here is replacing the electromechanical compressor. Sometimes this is referred to as the thermal compressor, where the refrigerant joins with an absorbent, water in this case, and goes into liquid form. That liquid, the pressure of that liquid is raised up to the high side pressure of the refrigeration cycle. And in order to get back to what we want, which is a high pressure, high temperature, pure vapor or near pure vapor, we need to boil off that refrigerant, and that's where the combustion energy comes in at the desorber. Everything else that you see here really is serving heat recovery needs to make sure that we have the most efficient process possible. And again, this is based on quite a lot of work by SMTI and their partners. A quick summary of the demonstrations that took place before this Los Angeles area study. First, it's worth noting that when we talk about field demonstrations, we have to distinguish between rated efficiency versus as installed efficiency. And the methodology that we like to use is the input-output methodology used for boilers and other types of heating equipment. And what we do with that methodology is we take on the horizontal axis the daily output, in this case hot water, and we estimate the delivered efficiency, and we draw those curves. And you're going to see some familiar equipment from a prior CEC effort looking at gas-fired water heating, where traditional storage products, they will have a curve that looks like this, reaching about 60% efficiency when we're really operating all the time. Of course, these curves decline as we provide less and less hot water, because standby losses and cycling losses become larger as a fraction of total delivered energy. We can look at condensing storage. We can look at tankless, which this is a little bit of more of a sharper drop off because we don't have quite as much stored energy there, and then condensing tankless as well. And then from prior generations, third generation units operating in the Pacific Northwest and the Southeast. We've had subsequent, or second and third, I should say. We've seen that once you get up to about 40,000 BTUs an hour, which is typical for a four-person household in most of the country, and we go to subsequent generations improving on that, this is where we see that 1.2 to 1.3 factor overall. Through these studies, we've also characterized the reliability. This is a new technology, and there are a lot of new custom components in use here. We've also characterized the efficiency with operating conditions. As a heat pump, its capacity and efficiency are influenced by not only the air temperature, but the tank temperature as well. And in fact, the latter is more important for this type of technology. So we've developed those performance curves and put them to use in projecting these efficiencies here. And also, this produces a moderate cooling effect. The evaporator, as it's drawing in energy from wherever the heat pump is installed, there's a small, about a 1 kilowatt thermal cooling effect there. And if you want it, that's how much it is. And if it's a nuisance, then it can be vented or exhausted if that's necessary. So now we're shifting into this project here. We performed a measured baseline of existing water heaters up front. And then we installed the prototype heat pump gas-fired heat pump water heaters in parallel. These were not intended to operate in parallel, but really just to have that backup in the cases that the prototypes needed to be serviced. So we would switch over from one to the other. In performing this study, we are looking at both the energy efficiency of the appliance, but we're also looking at key cycle temperatures within the absorption heat pump in order to better understand what's occurring with time or as faults are detected. Okay, there we go. Oh, sorry about that. Looking at the 5 sites that were selected here, these were all in the Los Angeles Basin. These are all fairly typical from the homes that we've had in prior studies. All of these are in garages as installed. We sought out homes that had a sufficient amount of occupants to have a high enough hot water demand for this size product. The tank on these products or these prototypes was 65 gallons nominal. So you can see that sites 1 through 4 have 4 individuals living there. And for the 5th site, we had 2 to 3 over the course of the study. Low efficiency products as baseline, with the exception of site 5, the 5th site, which had a power vent, a slightly higher efficiency product as baseline. One of the first things we wanted to do during the baseline measurement was get a sense of what the demand was. Is the heat pump water heater going to be overwhelmed by the load at these homes? And the short answer is possibly. This is something that we were trying to keep a close eye on. And it's important to note that on an average basis, these 5 homes had pretty moderate hot water usage, but each of them had very significant excursions over the 3 to 5 months that we monitored their hot water. And they could be for various reasons, multiple washing machine runs, new occupants in the home, and so on. But one thing we wanted to key in on was this behavior of drawing hot water to the point that it runs out, sort of taking that shower to the point that you run out of hot water. And we can do that by looking at the individual hot water draws and charting on a basis of the total volume of the hot water draw and the delivered temperature at the end of the draw. And you can see here that for some sites, this is pretty normal behavior. They use hot water as you would expect. But for 2 sites here in particular, the data points in green and the data points in blue, you see this decline with very large draws. And this is that kind of behavior we were looking at here. So we want to make sure we keep this in context when we look at hot water capacity going forward, just based on these behavioral elements. First thing we want to look at in terms of baseline, or second thing we want to look at in terms of baseline data is the efficiency. This is the yardstick to which we use to judge the energy efficiency here. And I'll just drive home the point before that we're looking at an as installed site-specific energy savings. They're using that input-output method here. And just to illustrate this further, for 2 of the sites here that had a 0.62 or 0.67 uniform energy factor products installed, this is what their delivered efficiency curves look like as compared to their rated efficiency here. So you can see that it really takes a very, very large draw for these to meet their rated efficiency here. So we'll be more in this realm here in the 50 gallon, 60 gallon a day department. There was a retrofit after the heat pumps were removed after a 12-month monitoring period, and each of the sites got high efficiency gas-fired products of their choosing, or chose high efficiency condensing tankless water heaters, and then one chose a storage type high efficiency product. One thing that's worth noting between the tankless sites is that there was a innovative recirculation loop employed where the furthest fixture was used to create a recirculation loop for the tankless water heater to limit the time to deliver hot water. Different types of controls were employed between the sites, and we were able to compare the results there as well. Looking at the second baseline here with the high efficiency, first of all, we look at the chart here, nobody's running out of hot water anymore. That's because these are the capacity is there to meet that demand nearly on an infinite duration. However, when we talk about delivered efficiency here, and I guess I apologize for some of the small fonts here, that these are pointing out the difference that the recirculation controls have on energy efficiency from these kinds of products. If no recirculation is employed, we're very close to our above 90% efficiency that we would expect here. But depending on how we use recirculation here, if it's timer-based or demand-based, we can degrade that, as shown. As we installed the heat pump water heaters, we had a couple lessons learned during the first few weeks of operation. Some things that we learned just worth pointing out here, the sensitivity of the combustion system to small changes in back pressure on the venting. So we needed to be very careful about properly sloping the venting at one of the sites to make sure that condensate would drain properly. Also, in terms of shipping the heat pumps from the Southeast to California, we did incur shipping damage in a few cases here that led to a design improvement with a couple of the units. And of course, there were also some design improvements made around the components, as this was really the longest field demonstration of this technology. This is a quick summary slide of what we saw over the whole period here. Over 20,000 gallons of hot water delivered, nearly 5,000 hours of operation between the sites. In some cases, very, very large hot water draws and a pretty wide range of ambient conditions with very hot and fairly cold for California conditions as well. This just gives you a sense of uptime, and there was a major overhaul of one of the components, the solution pump, that happened at this phase here for all units. First thing we want to look at is energy efficiency. We can see a little bit of variation between the sites, but if we include electricity and gas inputs to the heat pump water heaters, there's about, on average, a 54% reduction in site energy versus baseline. If we look at how this translates to CO2 emissions, this does again vary from site to site on a percentage basis, but you can see here that the baseline for each site shown in red, and the sharp reduction during the gas heat pump water heater phase, and then the same on a percentage basis. So anywhere from 65% to 20%, depending on the baseline. On average, 49% greenhouse gas emissions reductions. Kind of going a little deeper into the energy efficiency, we compare first to the original baseline here. This looks at the energy efficiency, or the natural gas savings alone versus the original baseline. And then we also look at the retrofit. So if instead of installing the gas-fired heat pump water heater, you install the high efficiency gas option. And even in some cases, due to the impact of that recirculation loop and controls, you can see that that does not result in savings here. Greenhouse gas emissions are shown here summarized, and we can look at, in terms of the first half of the demonstration and then the total demonstration, the comparison of delivered efficiency versus baseline here. And really, I would caution you to focus more on the difference here, which is shown here in savings, as opposed to the absolute numbers due to the impact mentioned before. Now, if we dive a little deeper and look at the COP of the heat pump component itself, so how efficiently is the heat pump capturing ambient energy and delivering it to the tank? We did see a very wide variation between the sites here. But really, if we group it a little bit based on some characteristics, the coastal sites saw a much narrower range of ambient temperatures. As a result, we saw COPs on average between 1.4 and 1.8 for each operating cycle. Those that are in the valley that saw a much wider range of ambient temperatures and also in some cases usage, they had a flatter and a much wider range of COPs. And of course, we did see some equipment issues that drew some of those values down, mostly having to do with the wear and tear on the various components. Also, we want to talk about electricity usage. The gas-fired heat pump water heaters are replacing products that in some cases do not consume any electricity at all. So we want to look at both under normal conditions, how does it consume electricity, and how is the supplemental heating used in those high demand scenarios. To answer the first question, it's about a half to 1 kilowatt hour per day, or if you want to normalize it, it's about 9 watt hours per gallon above a constant 23 watts. Typical power draw is anywhere from 100 to 150 watts. Keeping in mind that these are prototypes, and that number will go down with finished products. In terms of the supplemental heating, which is brought on in parallel to the heat pump, it's never brought on in isolation. This provides about 1 to 6% of the total energy output over the course, and you can see the range here between the sites over the course of the study. And one site I should have highlighted before did have it disabled because of some electrical distribution issues at site 3. And I'm going to hand it back over to Mary here to walk us through the remainder of the project.
Great, thanks, Paul. So I want to touch on a few other components of the project beyond the field evaluation. As I mentioned, Southern California Gas did some laboratory testing at their Engineering Analysis Center. This included performance testing as well as some accelerated durability testing. For the performance testing, testing efficiency per the DOE UEF standard. For emissions, of course, using the South Coast Air Quality Management District methods for carbon dioxide, carbon monoxide, NOx, and unburned hydrocarbons. The accelerated durability testing, basically you can do an accelerated operating life test and extrapolate that out for the full length of the estimated equipment life. And some spot checks were performed to assess the degradation of various key performance metrics, as well as the emissions levels. There are detailed results of this laboratory testing, as well as a review of the results of prior laboratory testing from earlier generations of this unit that were outlined in the forthcoming CEC report. For what it's worth, I'm showing that the deck is still controlled by Paul. Okay. As I mentioned, we also worked with our partners at Frontier Energy as well as Beyond Efficiency for the development of a simulation model. The simulation model was not intended to be a detailed research model, but rather a kind of straightforward, easy to use tool that a range of stakeholders could engage with. It is based on Python script, and it basically simulates any provided data set, including all of the 16 California climate zones, as well as the CBAC residential loads. It'll calculate energy use, operating costs, and carbon dioxide emissions. There are some key model assumptions outlined here. A validation effort was also undertaken to compare the modeled results with the monitored results that we saw in the field. We selected a 28-day period and found that the results were in agreement within an error range of about 5%. So we saw good confirmation there. Again, there is a more detailed description of the model development itself, as well as the results from it in the forthcoming CEC report. I did want to take a couple slides to talk about the market impact assessment that we performed. A two-step approach was used and developed with partners at Applied Research West, as well as with Stone Mountain Technologies. We began with a qualitative step, which consisted of in-depth interviews with over 24 plumbing, HVAC, and home energy improvement contractors. We then followed that with 4 focus groups, professionally moderated in California, with over 40 participants. Based on the discussions and perspectives gathered over that qualitative step, we then developed a quantitative survey, 2 actually, that were executed nationwide, 1 targeting specifically contractors and 1 targeting homeowners. We developed a very high-level SWOT analysis, so that's strengths, weaknesses, opportunities, and threats, to help kind of understand the most compelling features, the most challenging barriers, and where there's opportunities for improvement here. So that's outlined here. I do want to be sensitive to the time, so I'm going to move forward because I want to allow time for questions at the end. I wanted to just highlight a couple of key findings. In our qualitative interviews as well as focus groups, the majority of contractors indicated that they felt they could sell the product. When asked about the biggest barrier, not a surprise with any pre-commercial technology, but the initial cost was cited as the primary obstacle to consumer acceptance. Based on the responses received from homeowners, we determined that approximately 1/3 of single-family households that currently have natural gas or propane service were likely to be prime customers for this technology. Here's sort of a demographic snapshot of what that prime customer is most likely to look like. Ultimately, this target audience indicated that they were more likely to purchase the gas heat pump water heater over other commercially available water heating options, provided that the purchase price difference was $1,000 or less. So that sort of shows the maximum premium price that this target beachhead customer would be willing to accept for this technology. One of the things we did ask, we sort of broke down regionally, asking consumers to indicate their preference for 3 different water heater types. We included a standard tank, a tankless, and a gas heat pump water heater. We gave various survey respondents different price points to deal with, to look at sort of where that price sensitivity lay. I think the takeaway from this slide is that you can see, first and foremost, we saw a very high percentage of consumers that expressed a preference for the gas heat pump water heater when the features were outlined. But you can also see that there is clearly some regional variation. You know, certainly we've got Southern California, where we have very mild climates and low water heating loads, and we see some of that change. There's a variety of influences at play here, local utilities, conditions, expectations of the consumer, and so forth. I also want to compare this graph with the next one. This graph shows what we deemed small domestic hot water consumers. These are folks that have 40-gallon tanks or smaller. This certainly represents the majority of consumers, but we did also separate out those consumers that have larger tanks. I think the interesting difference here, of course, is basically once you move into these larger consumers, into this category, you see a much higher jump in the preference for the gas heat pump water heater. Again, kind of speaking to that economic play that can be made for larger consumers, where their annual savings are more likely to offset the initial cost initially. You also see sort of a shrink in that spread across regions, again, sort of speaking to the fact that these become more economical for those users that consume more hot water. So ultimately, as I mentioned, 6 pre-commercial hand-tooled gas heat pump water heater units were successfully commissioned in California, 5 at single-family home sites and 1 at Southern California Gas's research laboratory. As Paul mentioned, we did receive South Coast Air Quality Management ultra-low NOx certification through the project, and saw certainly very strong annual average gas savings compared to the baseline, the initial baseline, as well as the second baseline. Over 12 months of operation at the sites, very strong COPs in the range of 1.25 to 1.6. 4 out of 5 of the surveyed homeowners indicated that they, in their perspective, that they never ran out of hot water. So strong performance there. And certainly the laboratory testing performed by Southern California Gas confirms the feasibility of achieving that 1.2 UEF target. As with any research project, there's always another next step, another place to go. As was referenced earlier, there were a couple opportunities to improve reliability of these units, some key design changes to avoid damages related to shipment, as Paul had mentioned. We did also see some variation in performance between sites. Some of this is explained by site and usage variations, but also, as I mentioned, these are hand-tooled prototypes, so there is some variance in prototyping quality. The installation requirements, there are some potential site challenges related to venting. Electrical service, as Paul mentioned at Site 3, was a challenge, and space requirements. These units do have a different form factor than many of the conventional water heaters on the market. So really cementing technician commissioning procedures would improve this. And then also some further product development needed to address the supplemental heating and how best to address any concerns around domestic hot water capacity. I will briefly mention that we also have a follow-on effort that kicked off earlier in 2020. This is a multi-sponsor effort. We have 8 utilities that have come together to form the North American Gas Heat Pump Water Heater Demonstration Collaborative. They're targeting the installation of about 50 gas heat pump water heaters across 5 regions in the US and Canada. So that is a project that's just got underway this year and is really building on the successes of this research effort funded by CEC and SoCalGas. And with that, I will turn it back to Matt to field any questions.
Thank you, Mary and Paul. That was a lot of information, but it's all good stuff and super interesting. I'm not showing any questions in the chat box yet, so to everyone watching at home, if you do have questions, please submit them through the questions box in GoToWebinar. I will go ahead.
I was going to say, maybe I can take this opportunity to say, as I mentioned, that CEC will be publishing the final report in the coming, hopefully in 2021. But I also wanted to highlight we have some additional resources on GTI's website. There's a link here. We have a one-pager summarizing the project findings, as well as some case studies of individual homes and a snapshot about the technology itself. So you're welcome to go there and get those documents today.
Yeah, thanks for that. I think that one pager is really exceptional. It does a good job of kind of summarizing everything we covered today and really making it easy to move through for, say, a layperson like myself. I will dig in with one question. What I'm struck by going through this project is it was more than just a technology demonstration. You know, you talked a lot about installation, lessons learned through installation, and talking to installers, but also the market study. I'm wondering if you could just give us a little color behind what was driving the expansiveness of this project to include those sort of market factors.
Sure, I can speak to some of that. Ultimately, you know, the gas heat pump water heater, it's not a new version. It's not this year's version of an old product. It really is an entirely new product category. So really understanding, you know, we've seen the electric heat pump water heater, which was introduced several years back and had kind of a bumpy road to introduction in some cases. And so I think this is a little case of hindsight, understanding that really having that market input up front to inform you about the likely barriers so you can kind of get out ahead of them before commercialization and kind of have a soft landing when the product is actually launched, and really cultivate market pull as well, you know, so that there is an established market once the product becomes available. I think we realized the critical nature of that. So the opportunity to include that research in this project, I think, you know, anytime you do field work, you're always having kind of a natural opening to at least speak to those homeowners. But we wanted to be able to expand that to a larger data set. And so the qualitative and quantitative efforts with the market research really allowed us to kind of get a bigger picture about what the market response might be to the technology.
Perfect, thanks. All right, so it looks like we're getting some technical questions in here. So first one is, what is the GPH or GPM recovery rate for the product?
Maybe that could be framed as a first hour rating. And as a heat pump water heater, it has a slower recovery time. So for a lot of the sites, the heat pump water heater was replacing a gas-fired product that had about 3 times the output of that from the baseline. So in that regard, the first hour rating is really a function of the tank size more than anything else. So take a few gallons off the tank size, and that gives you an indication of how much hot water you can get per hour. And this is a feature of heat pump technologies broadly, not specific to this technology.
Okay, and how about what was the baseline efficiency for the 5 sites based upon?
That was as measured. We had monitoring equipment in the 5 homes for a period of about 3 to 5 months, depending on when the heat pump water heaters were installed.
How does the gas heat pump operating cost for the consumer compare to an electric heat pump?
We did not really extrapolate beyond the California region, nor did we do an extensive comparison with gas versus electric products here. We do touch on that through the modeling that Mary alluded to, which will be available in the reporting. But the short answer is it depends. It's highly dependent on what your local utility rates are and how the heat pumps are operated.
So here's a question. Are the CEC or the gas utilities working on market incentive programs for this GHP technology?
Well, I won't claim to speak for Matt in Southern California Gas, but I can certainly say that through the North American collaborative that I mentioned in one of those latter slides, primary interest of the utilities was to develop rebate programs that would be there, ready, set up, and available upon commercial launch of the product. So I can safely say, we saw both U.S. and Canadian utilities interested in putting programs into place for basically the moment the product becomes available for sale. I don't know, Matt, if you would want to add anything further.
No, I agree. It's a key component of the research we're doing with all of these technologies is to try to collect data that will help inform rebate programs or utility programs. And as you said, we want to soften the market. We want to be ready with the programs in place when the technologies are available to the consumer. Let's see. Generally, what was the homeowner's perception or experience with the technology? Could you expand on some of the feedback that they provided?
Sure. So we did do a pre and post survey with the homeowners. We did want to understand their specific reaction to the technology. I would say, as I mentioned before, overall, we had really positive feedback from the homeowners. I had some numbers, I'm afraid I don't have them handy right now, but 4 out of 5 of the homeowners indicated that they never ran out of hot water or had performance issues. So all of those homeowners indicated that they were satisfied with the performance. We also asked them about noise and comfort level. Being a heat pump, there is a certain amount of heat draw from the ambient space. All of these units were placed in garages, so it wasn't of primary concern, but we did ask and see if this was noticeable or if there were any concerns around the noise. And we received positive feedback on all counts. So we didn't have any complaints around noise or comfort level or performance.
Great, thanks. And then I think this will be our last question, but was standby loss calculated?
Yes. And probably they want to know what it is. I would encourage the reader to, or the questioner to follow up with us. We can provide details. Just to give a little bit of color to that dodge there, the standby losses were higher than a finished product would have. And that's mainly because a standard electric storage tank was used in the construction of these prototypes. So there were a lot of additional connections and I guess points of thermal loss that would otherwise be eliminated. Additionally, for our instrumentation, that would be eliminated in the finished product.
Great. Jackson, do you have any sense for when the final report will be available with all of the details? Sometime next year?
Yeah, sometime in 2021. I don't have the exact time frame beyond that, just because our publications process could take few months for it to go through all the reviewers and the edits and stuff like that. So sometime in 2021. Yeah, if you guys want to follow up with me about when it might be published, just feel free to reach out to me and I'll try to keep you up to date about when it comes out.
Yeah, and so for everybody viewing, if you have additional questions or additional feedback, please feel free to send us an email at rddinfo@socalgas.com. We look forward to your feedback and your questions, and we'll try to provide some more detail. And then obviously the full report will be available next year, a comprehensive report for the public. With that, we're at our time limit. I want to thank Paul and Mary for a great webinar. We're getting really good feedback in the chat box. I think people were really excited to see this information and learn more about this technology. And Jackson, thank you for joining us, and thank you to the CEC for supporting this research as well. So with that, I will say thank you, and everyone have a great afternoon.
Thank you, everyone.
Thank you.
Bye-bye. Thank you.